Hello and welcome. This will be the practical implementation of Delta Lake using Databricks. So without wasting time, let's get started. So the first thing we need to do is create a new resource group. So let's go to resource group and here let's create a new one. Now let's give the name Delta Lake resource group. It should be available. Now let's select the region, Central India. Now click on review and create. Validation passed. Now click on create. This will create our resource group. Now let's go to the resource group. Inside the resource group, what we are going to do is create a few resources. Now, the first one will be a storage account. It will hold the raw data as well as the metadata or the meta store. So let's search for storage account and select Microsoft storage account. Click on create. Now resource group is already selected. So let's give a storage account a name. Delta Lake storage account. It's available. Now select the primary service. The default one is fine. Performance standard, redundancy, let's select locally redundant. Now this will, by default, it creates a blob storage, but we want ADLS or Azure Data Lake. So what we can do is go to advanced and select enable hierarchical namespace. So this will enable the data lake storage account. Now go to review and create. And after a few validation checks, we will be able to create a storage account. Now click on create. Our deployment is currently under progress. Let's wait for it. It will take only a few seconds to create the storage account. Our storage account is now created, and inside here we need to create a few containers. So let's go to resource, go to containers on the left hand side. Now the first container name will be raw. It will store the raw data, and the second one will be meta store. So this container will be used by Databricks, and I will explain it later what it will be doing. Now the next thing we want to do is create our Databricks. So let's go to our resource group and now go to create and let's give Databricks, and here it is. Select Azure Databricks and click on create. Now let's give our Databricks workspace a name. Give Delta Lake DB Databricks. And we can also give a name for our managed resource group, but that let's just give it. It's all right. So managed resource group for Databricks. This is fine. Now go to review and create. And after a few validation checks, let's click on create. It will take a few minutes to complete the deployment process for the Databricks. Let's wait for it. The deployment for Databricks workspace is now complete. Now let's go to resource and let's launch the workspace. Let's wait for it to sign in. So the first thing we need to do inside the Databricks workspace is catalog, and we need to create a Unity Megastore that will attach to this workspace. So let's wait for it to complete and then we will move forward. And here is our Databricks workspace. Now the first step is to click on this drop down, and here you can see we are not getting the manage account. So let me show you the procedure on how you can get that. What you need to do is open a new tab and go to accounts.databricks.net. Sorry, it's account.azure Databricks, really, Azure Databricks.net, and we will sign in here. So what we are going to do is open this link accounts.azure.databricks.net in an incognito tab so that we can get the login, because if you directly log in from here it will go back to the same page. So let's cut this link and open it in a new incognito tab, and let's paste it here. Now click on Microsoft Entra ID and it will ask you for the ID password, and what ID password you're going to use. So let me show you. So go to Azure portal and let's wait for it. Inside Microsoft Entra ID, go to users, and from here select your user, and here you will see a ID that will have hashtag in the middle of it, and use a password that you already know to log in. And I will show you what it looks like after logging in. After logging in, it will look something like this. You can see account console, and on the left hand side you will see workspaces, user management, etc. Now what we're going to do is go to catalog, and here you will see the auto created catalogs we already have. And what we are going to do is delete the auto created meta store, which will be in our region. So I have selected Central India, so make sure to delete this one. So click on it and click on delete. Let's give the name and delete. Now what we are going to do is create a new catalog. So let's create a meta store. Let's give the name Delta Lake Catalog. This is fine. Now let's select the region, Central India. Now we are going to provide the ADLS Gen 2 or the path. So what we are going to write inside here is, let me show you. So the path will contain the container name first, which is, let me show you, and we open it in a new tab. So let's go to our resource group. Inside, this is our storage account and the containers. The name of the container is metastore. Let's copy that. And then we will need to give the name of the storage account. So let's copy the storage account. And after that, what we're going to give is dot dfs dot o dot windows dot net, and now it should be fine. Like currently there is an issue, so it just needed a slash in the end. Now what we're going to do is get the access connector ID. So what we have to do is uh, provide the contributor role to Databricks to access the ADLS Gen 2, and before that we need the access connector. So how to do that? So let's go back and let's go to our resource group. So this is our resource group. Inside that we are going to create a new resource that is named access connector for Azure DB or Azure Databricks. So let's search the marketplace, access connector. Here you can see access connector for Azure Databricks. So we are going to be creating a new resource. Let's create one. Now let's give the name and just give it, okay, Delta Lake access. Now select the region, Central India. Now click on review and create. So we have to assign a role of that will be the storage block contributor role to this access. And so how we going to do that? Our deployment is successful. What we are going to do is go to our storage account. So let's go here, and here is our storage account. So inside the storage account on the left hand side, go to access control IAM, and then we are going to add a new role assignment. And in here we will search for storage blob contributor. Let's wait for it. and let's search storage blob. Here you can see storage blob data contributor. Select this, click on next. Now go to managed identity. Now let's select the members and let's search by, okay, here you can see access connector for Azure Databricks managed identity. Now we will give the name what we gave, Delta Lake Access. Now click on select and the rest all is fine. Now click on review and assign. So let's review and assign. It will take a few seconds. Our role assignment is now been added. So what we are going to do is get the access connector from the connector we just created. So let's go to resource and in here we will copy the resource ID. Here you can see the resource ID. So let's copy it and we will paste this in here. So let's paste it here. Now this all looks fine. Now click on create. Let's wait for it. It will take a few seconds. Now what we are going to do is assign this to workspace. So what we can do is um, let's leave it here. Let's go back to Databricks. Let's refresh. And now let's go to catalog. In here, let's assign it to Delta Lake DB workspace. And now let's click on assign. So it will enable the Unity catalog. Let's enable it. And congratulations. Let's just close it. Now let's go back here. So you can see, let's refresh. There will be a new workspace. Now what we are going to do is go to configuration and here we have the Metastore admin. So you have to edit the hashtag account from here to the normal account because that's the account we are using the Databricks with. So our most of our groundwork is now done. What we need to do now is go to the Databricks workspace. So let me open it again and it will take a few seconds. So now what we're going to do is create a new compute or a new cluster. So go on to compute. Now let's create one and the default name is fine. Let's select a personal compute. It's all right. So Databricks runtime, let's select 15.4. Node type, the standard D3 is fine. So how long after inactivity? Let's give 100 minutes. Okay, so numlock 100 minutes and rest all is fine. Now let's click on create compute. Now what we need to do is create a new catalog. So how we do that? So go to catalog and in here what we are going to do is click on this plus. Okay, we need to create a new catalog. Plus add a catalog. Now let's give the catalog a name. Let's give Delta Lake catalog and let's just give one. The type will be standard. Storage location just leave it blank. Now click on create and configure our catalog. This all is fine. Click on next. Let's select the key. So we need to select our key. So we do not need to do anything here. Just click on save and our new catalog will be created. So now our Delta Lake catalog has been created. So we need to add the external data. So how we do that? Click on the catalog button and here you can see an option external data. So we need to create an external location. Why? because we need to define the external location to get our data from, which will be the raw container that we created in our storage account. So let's give that. So let's give any location. Let's give raw, and let's give the path abfss colon double slash raw and the storage account name. This is the storage account. It is colon at the rate storage account, then dot bfs dot code dot windows dot net, and storage account credential that we created. Let's select this and now click on create. Now we are good to start and creating our notebook and everything else. Let's see if our compute is done, and our compute has now been created. So in the next video, we will create a notebook and everything else. Thank you. In the previous video, we laid the groundwork for our Delta Lake, and now we are good to start with creating our notebook. And so let's start with it. The first thing we need to do is create a new workspace, and here you can see we have our Delta Lake catalog. So let's create a new workspace. Click on workspace, and here you will see the option create, and creating a folder will actually create a workspace. So let's give a Delta Lake workspace. Let's also copy the name. Now click on create. And inside this new workspace, what we are going to do is create a new notebook. So create a new notebook. And the first thing we need to do is let's connect the compute first. And let's also rename. Let's give one Delta Lake. And the first thing will be to create a manage table. So let's give a small heading as create managed table. And so before creating a managed table, what we need to do is create a schema. So let me show you what schema we have. Let's open catalog in a new tab, and I will show you our catalog. So we have a catalog named Delta Lake Catalog 1. And what we are going to do is currently we have default and information schema in it. So which is basically the default values. So what we need to do is create our own schema. So let's copy the name of Delta Lake Catalog, and let's add a code block on the top, and let's give a small heading as let's give just schema, and let me give you the command for schema. So write percentage SQL and create schema, and we have to give the name of our catalog and then the name of our schema. Let's give the name as raw. Let's run this. This will create our schema inside the data lake catalog, and let's wait for it to run properly. Then what we are going to do is define our schema. Let me refresh it here. You will be able to see. Here you can see the raw schema is now created. Now what we're going to do is create a manage table inside the schema. So we will use the percentage SQL, and on the next line create a table. So as you already gave us, so delta lake catalog one dot raw, and then we have to give the name of our cat table. So let's give managed. Let's also use managed raw table, and in the next line we will define our schema. Let's give ID as int, and order name. This will be string, and let's give amount. This will be double, And let's give product ID, and this will be int. Now we need to define like which format we are using while creating our table. So let's give, it already gave us using delta. Yes, that's what we are going to do. So let's run this as well. So this will create our schema for the manage table, and let's wait for it. It's running the Spark jobs. It will take a few seconds just creating a table. And here you can see Spark job ran successfully. Let me also show you in here. So inside the raw, you can see manage raw table. And in here, you will see the schema. Let's close this. Here you can see ID, order name, amount, and product ID. Now let's insert some data into the table that we just created. So onto the next cell, type percentage SQL, and pretty simple SQL commands. Insert into, and then it will automatically give the table name. Let's give values. Let's let's give any name what we want. Let's give mobile, and the next thing what it is, amount we have to give. Let's give 100, 1001, and now we have to give the product ID. Let's give 655, and let's add a few more rows. Price, and now the third one. Now let's add these values. So, so you might be thinking that how is this different from your normal SQL database? Actually, the thing is that this data is stored in file format instead of traditional database. So I will show you that later. So before that, let's also uh, display this data. So percentage SQL, select star from italic raw table, and here you can see the word data is present, mobile, TV, fridge. So let me show you. So go to Catalog Explorer. Let me just close it and open it again. Open Catalog Explorer, and here we'll go to our catalog that we created, which was Delta Lake catalog. And inside the raw schema, we have our managed raw table. This is the detailed information what we get from out here. So let's go to details, and here you can see the storage location. It is stored in the meta store container inside our storage account that we created, and this is the table name and rest all stuff. Let me show you this as well in the storage account, and we can close this. So here you can see, go to containers inside meta store. Here you can see we have tables, then we have folder. Here is our part file, which will be in, you can see, parquet format. So it's not, definitely not an traditional database. So let's also show you the logs. Here you can see the logs. Now let's also create an external table. So go back to Databricks, and let's give a small heading first. let's give mm, let's give create delta table, and in this time we will create the external table, and let's run this. Okay, now what we're going to do is create an external table. We will pretty much use the same command, so let's copy it, and here you can see there will be a few differences. Let me first paste this command. Let's also change the name. Let's give external, and this time what we're going to do is define a location. So our location will be the raw container that we have inside our storage account. So let's give abfs abfss colon double slash then raw and the name of our storage account and dot dfs dot o dot windows dot net, and inside here we want to give a new container, sorry, new directory. Let's give it the name as external underscore raw or just external underscore table. Now let's run this. Okay, there is okay, raw at the rate. My bad. Let's run this again. Just a small space here before that. No need to worry. Now let's also add the same data in here as well. Okay, so here it is. Let's copy new cell. Let's change the table name external. Now let's run this and let's query this data similar format, and let's change the name. And here you can see pretty much the same data, but this time what is the difference that it is inside our raw data container. So here you can see it's still in the parquet format, raw data container. So let's move on. Now, so we have queried our data using the X table. So this is one way of querying the data. Let me show you another way of querying the data. So how we can do that. This is a special thing in Delta Lake. So what we're going to do is type percentage SQL, and this time we will not give the table path, but what we are going to give is, let me show you, from, and then we will give these. So these are not single quotes, but what it is, it's button up directly above the tab, and inside here what we are going to give is the path to our external table that we gave up here. Here you can see the path. This exact path what we are going to do is give inside here, and let me run this. So this will display the, don't worry, this error is pretty simple. The thing is you have to give delta dot abfss then the path. Now let's run this. Here you can see the same data, it's present here, and this is how we can query it in another format. And that's all for the next video. In this part of the video, we are going to learn some other methods of creating delta tables using Databricks. So the first method we are going to learn is called CTAS, which is the method for creating tables using existing tables. So let's first give the heading, and this is the method name. And in the next cell, we will write the command. So the command goes pretty simple. It's SQL, then create table, and we will give the name of the table, so which will be delta like catalog dot raw dot external table, and then let's give ctas. Okay, let's give it in, and what we want is to get data from a pre-existing table. So select star data from, not this, and we want to get the data from the Delta Lake catalog one dot raw dot external table. Yes, that's where we want our data from. Also, we will provide the location where we want to store this table inside our storage account. So we will be using the using delta method, and then give the location as single quotes ABFSS. So we can copy this path from up here, and in the end we will change the directory name. So let's give external table cetas. So the path is the raw container, then our storage account, and then the directory named external table cetas. So let's run this, and it has successfully been created. So let me show you inside the catalog explorer, and let's refresh. Our external table cetas has been created, and here you can see the ID, order name, everything. The schema is same. And let's also go to the details. Here you can see the ID and the storage location. So let's go to the next method of creating. And so what this one was, we created a table without using any DDL command, and we copied data from one table to another directly. And the next thing we are going to learn is cloning in Delta Lake. So let me give the heading for that, percentage MD, and cloning in Delta Lake. And so there are two different types of cloning in Delta Lake. The first one is called deep clone. So let's give that as well, percentage MD. And I will explain deep clone what exactly it is. And let me close this. Can expand our catalog from here as well, but that's not issue. So let me give the command percentage SQL, and then create table. Then we will give the name, the catalog name, and external table underscore deep. And what we're going to do is create a deep clone, and from where we want our deep clone is the external table. So let's run this, and this will create a deep clone of our table, and we will compare it with the shallow clone as well. So next step is shallow clone, and our data has been done. Now let's move on to the shallow clone. Let's give percentage MD and shallow clone. In here, what we want is, let's copy the same command we did up here, and we will use this only. So we will just change the name. Let's give it shallow, and in here we also give shallow clone. And running this will give an error. Why? Because shallow clone can only be created using the managed table. So we already have a managed table. Let's get the name of the managed table, and then we will use that. So inside raw, our managed table name is managed underscore raw dot underscore table. So which is managed underscore raw underscore table. So let's run this. Okay, table cannot be So I accidentally removed the raw, and now let's run this. Now here you can see our data, our shallow clone has been created. So let's go to Catalog Explorer, refresh. Here you can see external table deep, external table shallow. So the entire schema as well. So let's go to details, and remember the table ID of shallow starts from 34B, and deep, let's get the table ID as well. It's BE35. So if we go into the raw container and go into external table, this is the original external table. We want to go into, okay, it's not refreshed, that's why we are not getting. So why we are not finding these shallow clones and deep clones? Because these are actually stored in the meta store. So let's go in here, tables, and where you can see the deep table has BE35. So let's go to BE35. Inside this, we will find both the log and the parquet file. So you can see delta log and the parquet file. And when we go inside the other one, that was 34B, we will not find the parquet file. So what it means is that whenever we try to query the data from shallow clone table that we created, so it will read the data actually from the managed table or the managed raw table, and whatever change is made in this table will be reflected in the shallow clone, and it is written inside the delta log that read the data from managed table, then it will work. So that's all for this video. Thank you. This video will be about DML in Delta Lake. And in the previous versions, what we did was create some external tables and some deep clones as well. So in this part, I have created just another notebook in the same workspace. And let's get started. So let's rename the notebook as to Delta Lake, which will be the second Delta Lake notebook. Now we need to perform DML operations. So let's give the heading as DML, DML in Delta Lake, or just DML in Delta tables. So DML contains of update, delete, remove, and drop operations. And so what we need to do is turn off the deletion vectors, and so we have to create an external table. So what we can do is copy the query from the previous notebook. So let's copy the external table. Okay, this is for deep, and this is cetas. Here is the external table. So let's just copy it and we will rename it. Let's give here external table and DML, and also change the location. So let's give external table DML. Let's run this. Okay, compute was not selected, so it will automatically be selected. Our external table for DML was just created. So now let's also insert the data. So let's copy the same command and let's change the name. So it's DML. Let's insert the data. So now let me also show you the data. So percentage SQL, select asterisk from Delta Lake catalog dot raw dot external table DML. Let's run this. Pretty much the same data, nothing new. So what we have to do now is turn off the deletion vector. So let me first give the heading and vectors. And how to do that? So open Google in a new tab and type deletion vectors in Databricks. And here you can see, go to auto enable deletion vectors. Okay, not exactly this page. We have to get the command to turn on and turn off the deletion vectors. Let me find it. And it's in the Delta Lake documentation. Here you can see alter table, table name, and deletion vectors equals to true. This is the command for turning on the deletion vectors, but by default now Databricks workspace has enabled the deletion vectors enabled for all the workspaces by default. So what we can do is copy this command and change the true to false. So this will turn off the deletion vectors. And let's also give our table name. So Delta Lake catalog, raw external table DML, set table properties, and enable deletion vectors. Let's also change the name. Now let's run this. Okay, so let's change the value from true to false, and let's also give the table name, which will be delta lake catalog dot raw dot external table dot dml. So let's run this. This will change the deletion vectors properties from true to false. Now our deletion vectors have been turned off. So what we can do is update in DML and update using DML from the table we created. So let's give a new heading and let's give DML table and let's run this. Okay, it's MD actually. Now we are going to update let any one of the values. So let's use SQL, percentage SQL, update, and delta lake catalog dot raw dot external table DML. Let's update any. Okay, it has given us a predefined value. We can also use that set amount equals to 1000 where ID equals to 1. So it will change the amount of mobile from 1001 to 1000 and on the basis of the ID. So let's run this. And let me also show you the data now. Percentage SQL, select asterisk from delta lake catalog raw.external.dml. So okay, here you can see our value has now been changed 1000. Earlier it was 1001. So there is some change made, and so what happened was, let me show you. Let's go to our storage account and inside the raw, here you can see external table DML. Here you can see there are two files. So what exactly does it mean? One was created at 4:50:58 and another one at 4:55:17. So what it means is that instead of updating the data in the original or the previous Parquet file, which was created at the earlier time, and it created what is called a tombstone. And so it changed the value inside a tombstone, making a copy of the file and changing the value in there. So what happened is it doesn't change the original file, but rather create a tombstone for the new data. And this process is called tombstoning. And how does it know where to read the data from after updating the data? So it's all written inside the delta log. So let me also show you that. Here inside the JSON files, and it everything is written like what operations were performed and what all has been done till now. And make sure to never delete or edit these JSON files, otherwise your processes will be a lot complicated become. So what I can show you, so let's open the JSON file, go to edit, and here you can see what it did first. So the first operation we performed was create table, and enabled data vectors were already enabled. You can see enable data vectors as true. So automatically, I told you that deletion vectors are automatically enabled in whenever a new notebook is created. So here you can see. Now let me go back to the second one, external table DML, delta log. Let me show you the 001 JSON. Here you will see, let me edit, and the operation was right. I appended some data, and in the notebook ID, cluster ID, pretty simple, amount, zero, and everything else. So inside the third one, you will see that I have turned off deletion vectors. So 00, okay, 002.json. Let me edit. And here you can see set table properties. The operation we performed was set table properties. Let me show you in here. Command also included the set table properties, and we converted the enable deletion vectors to false. So here you can see delta enable deletion vectors to false. So that's how it will know that our new change has been made, and make sure to read from what file and what data is to be read. Now here you can see I performed an update operation, and it's all stored inside the delta log container. And that is how it knows where to read the data from, where to fetch the data from after a new file has been created inside the external table DML container. Here you can see two files. One was created at 450 and 455. So it will automatically know that which file to read from after querying the data. At the end, here you can see it read the updated data. So that's how it knows. Now let's perform another DML operation on our data. So let's say the next operation be delete operation. So delete. Okay, so we have to give two stars here as well. No, this doesn't work. I don't know why. It's all right. This should be fine. Now let's perform the delete operation on our data. Let's say we want to delete the column where ID equals to 1. So delete from, okay, from delta lake catalog where ID equals to 1. Let's run this. So this will also create another Parquet file for our newly updated data, and it will also create another JSON file. And let me show you. Let's refresh. Here you can see a new Parquet file at 510 has been created, and inside the delta log a new JSON file as well. Let me show you. Here you can see it has removed the previous version of the Parquet file that we were reading, and then added a new Parquet file, which will be the new Parquet file with the updated data. So what it does is every time you perform a new operation, it creates a new Parquet file for the data and also a new JSON file. And how it reads the JSON file, it starts from 0 and then moves to words 1, 2, 3, 4. But you will be thinking that every time we perform an operation, it will create a new JSON file and it will have to keep reading 1, 2, 3, 4 up to the latest. But that's not exactly how it works. So whenever the operations turn to 10, so 0 to 9, so it will create a JSON file for the all 9 operations, and the 10th operation, sorry, that 11th operation, which will be numbered as 10, will only read the one JSON file which will contain the summary of all the operations from 0 to 9. And this will same will happen for 19, 29, and so on. So now in the next part, what we will do is turn on the deletion vectors, and we will know what will happen to the Parquet files and how it will work. in the next video. Thank you. In this part, we are going to learn what will happen if we have the deletion vectors which are turned on by default. So what happens when we add data, delete data, or update any data into our tables. So let's learn how and what happens. So what we are going to do is create another notebook using our Delta Lake 2. So what we are going to do is go to workspace and clone our 2 underscore Delta Lake. Let's clone it. Now let's also rename it. Let's give it, let's say 3 underscore Delta Lake. Now let's create it. Let's open it as well. Now what we're going to do is create another table for let's deletion vectors. So let's rename the table and let's also change the location underscore deletion vectors. Let's run this. So our compute was automatically connected. That's all right. Now let's wait for it to run. So our new table under the name of external table DML deletion vector has now been created. Now let's also insert the data into it and it's done. So this time what we're going to do is not turn off the deletion vector. So what we can do is delete this and let's also change it. Let's try turn on the deletion vectors, which is actually done by default. So now let's update value. Let's give the same and our new value has been updated. And so what will have happened in the raw container? Let me go back. So pretty basic, a new directory has been created under the name of DML deletion vector. And how many files should it contain? How many parquet files? Well, if the logic says from the what we've learned in DML, there should be 2 files because one was created with the original creation of the table and another should be with the updation of the table. But let's look. Here you can see there are 3 parquet files. One which was basically pretty simple for the creation while the creation of the table and updation of the data. Now what are the second file and the third file? Let me show you. So the first file basically the one will have the data initial format, and the second file actually what it has is the updated or the deleted or the newly created data or the whatever operation we are performing in the DML. So let's go back to deletion vectors document. Let's learn what exactly is deletion vectors. So deletion vectors are storage optimization feature that can be enabled on the Delta Lake tables. Now it has been auto enabled, but I guess the documents have not been updated. So by default, when a single row in a data field is deleted, the entire parquet file containing the record must be written, which is what happened when we turned off the deletion vector in here. So enable deletion vectors to false. This is what happens. So every time a new record has been written, deleted, updated, added, a new parquet file is generated. So which is okay for our case because our files are pretty small, like a few KBs. But let's say your parquet file is in GBs. So creating a new file every time a data has been updated or rewritten, that is a pretty big issue. It causes a lot of space to be wasted. So with deletion vectors enabled for the table, some delta operations use deletion vectors to mark existing rows as removed without rewriting the parquet file. So what it means is that only the updated, deleted, or the added row has been marked as deletion vectors so that a new file has been generated for those. So this file, the second file that has been created, will only contain the update we made in the table. So this update we made where amount was changed from 1000 to, sorry, 1001 to 1000. So this file, this, let's close this. Uh, this second file will only contain the updated column. So let me show you that as well. Let's download this and let's go to Parquet viewer. I just open anyone. Let's choose the file and okay. So this has all three files. What exactly did I open? And so let's open this one. Download. Me also show you. The second one will download it. So here you can see it only has one column. So it has the updated column. So it means that whenever you update or add or delete a data in the file or table that you have with the deletion vectors enabled, it will only make a change when a new Parquet file, and that file will be reflected and read whenever you are trying to query the entire data. So now what is this third file? Let me show you. So this third file, so this file is actually the combination of both of these bottom files. And why it has been created? Because it's always easier and faster to read from one file rather than reading from more than one file. And we will learn about it in detail in the next part of the video. And this thing is called the optimization techniques. So that will be the part of the next video we have. So let's also show you the delta logs. So here you can see pretty simple. The 00 will contain the creation of the table. 01 will contain the addition of data. Let's see what 02 holds for us. We can go to edit, and here you can see it has removed one part which was the original part and added two parts which were the updated column and the previously updated column. So let's also go in the end and let me show you here. So deletion vector storage type, and it has optimized it. So this is what it has been doing for us in the background by with the deletion vectors enabled. So let's also show you the final edit, and it has removed both of these part files that it added in the previous step and added the combined and the merged file so that it will only read from one file, making it much more efficient and optimized. Now here you can see the storage type. This was the previous file and it has inserted this file, the new one, with the optimized target size. Wait, but you got the point to the optimized target. So now in the next part we will learn about the vacuum. In this part we are going to optimize our delta lake table in Databricks. So our goal is to improve the query performance by optimizing how data is stored and distributed, especially after multiple writes. So what we are going to do is write our data or insert our data again and again to create multiple partitions or multiple Parquet files inside our raw container. And, and then we are going to optimize along with techniques such as Z ordering. So the first step is to insert our same data again to generate more Parquet files. And we will be using the same command that we did earlier. Let me show you. So we are going to use the to underscore delta lake notebook for that, and we have the external table DML, and we are going to update more data into it. So let's just copy this and go to the end. And what we can do is just try to run this like 3 4 times so that more files have are created. And here you can see it ran successfully. Let me show you. I have ran it already like 4 5 times, so there are like 6 7 files that have been created. Now what we are going to do is, and so what this does is append our new data into the existing tables and resulting in much more Parquet files that will be created in the underlying storage. So the first technique we are going to perform is Z ordering. So what Z ordering is, it is a technique that optimizes the physical layout of data based on the values of specific columns, and it helps with skipping data and improves the query performance, especially for large data set. So supposedly we only have like 10 files maximum right now, but in an actual production environment what you could have is like hundreds or thousands of file. So we perform Z ordering on columns that we often filter or query on. Let's say for example, right now we have 4 columns that are production ID or the product ID, the name, the amount, and something else. So what we're going to do is filter by the product ID or by order name. So we can use Z order on these columns. So to Z order your delta table, what we are going to do is write a query for that. Now let me show you. Let's also give a heading first for specific Z ordering. Okay, my bad. Don't worry. Percentage ND, double hashtag, Z order. Now the command for this is with SQL. Now, so we were going to use the optimize tag, and then we will give the name of our table, which is delta lake catalog, then raw dot external table DML. And what we are going to do is Z order by, so what column name we are going to use for the Z order, which will be product ID, semicolon. Let's run this. So this will Z order our data by the product ID. And in this case, you can change from product ID to, let's say, order name or something else, depending on your query patterns. So, so what exactly it did was combine all the partitions we had previously, like 6 or 7 of these, and then combine them and tombstone them, and to create a single partition that was the newly created partition, which is the latest one, and combined all of them and tombstone the previous one to create a single partition based on the product ID. So now all of the other partitions are useless for us, but we cannot directly delete those, which will cause problems. So we can delete them using Databricks only. So the next thing is to use the optimize command. So the optimize command reorganizes the data and reduces the number of small files in the delta lake table by coalescing them into a larger files. So this improves the read performance. So basically what it means is that it will create a singular file for all the smaller files we have, and we know that reading from one file is pretty faster and easier compared to reading from a lot of small files. And if you want to run the optimize command on your table, we can do this as follows. Let me first give a small heading, okay, MD, and optimize. Now command is also pretty simple. Optimize, okay, I forgot to give percentage SQL, optimize, and then the catalog, delta lake catalog dot raw dot external table. So this is all the optimize command is. So what we are going to do is This command will merge smaller files into a large file, making the reads much more efficient. So let's run this. So why perform these operations? So optimize. So what it does is reduces the number of small files by compacting them, which helps with the read performance by reducing the overhead in query. So pretty simple, it's easier to read one file or two files rather than reading tens or hundreds of thousands of files. And what Z ordering does is it helps in much more efficient data skipping, improving the query performance when filtering on columns involved in the Z ordering. So we should consider a few things. Zero ordering can be very helpful and very beneficial for filtering on columns, but it comes with some type of overhead, and we only use it on columns that are frequently used in where clauses in DML. And optimize should be used periodically based on write patterns of your delta table. So frequent small writes can lead to many small files, which can hurt the performance in large data set. So what is the difference in basic optimize and optimize with Z ordering? So the basic optimize command recognizes the data in our delta lake table and by compacting them into smaller files into the larger ones. So this helps in reducing the overhead of managing many small files, which can slow down query performance due to metadata handling and file input output. So we have this use case. So this operation is useful when you have a large number of files that result from frequent writes or appends to a data delta table. It compacts these small files into larger, much more efficient ones, improving the query performance by reducing the number of files that need to be read. So it has this effect that it merges all the small parquet files into a large ones, and it improves the read performance by reducing the file input output and metadata handling. And it may be particularly useful after frequent insert or update operations, which can create multiple small files that degrade the performance. Now, what is optimize with Z ordering? So optimize with Z ordering is an additional optimization technique that comes with the physical layout of data in the table by reordering the data based on specified columns. So Z ordering helps with data skipping during queries, significantly improving the performance of queries that filter on specified columns. So the use case for this is that this operation is especially beneficial when your queries filter frequently on specified columns. So Z ordering helps to co-locate data with similar values in the same file, which allows Delta Lake to skip irrelevant files when querying. And this improves the performance for queries, let's say with where clauses. So the effect of Z ordering with optimize is that the data is physically reordered based on the values of the specified columns, which in our case was product ID. And it also improves the query performance, and it improves performance by enabling data skipping on during filtering on these columns. So this is especially useful for large data sets where queries are often filtered by a specific column like product ID or order name. So when to use each? Just optimize. We should use this when our delta table has many small files resulting from frequent writes like batch jobs, inserts, updates, deletes, whatever. And this will help us reduce the number of small files by improving the read performance. And when to use optimize with reordering. This should be used when you frequently query a table based on certain columns like product ID or order name. And Z ordering makes sure that the data is physically laid out to optimize fast filtering based on these columns. That's all for this video. In this video, we are going to be performing liquid clustering in Delta Lake. So liquid clustering is a feature in Delta Lake that is designed to manage and optimize data in large scale environments. It's part of Delta Lake's dynamic data management features that is aimed at improving the data storage and query performance. So, this clustering mechanism allows for efficient data organization and helps improve the performance of queries over time, especially when data is continuously updated or added to large tables. So, what is the purpose of liquid clustering? So, liquid clustering automates the task of organizing data in a way that enhances performance for certain types of queries. Unlike traditional static clustering, which requires you to specify partitioning or clustering columns, liquid clustering automatically adapts as the data changes. It helps you organize performance without needing to manually adjust the clustering as data evolves. So, what are the benefits of liquid clustering? The first one is improved query performance. It helps in speeding up read and write operations by clustering data based on query patterns. Second is cost optimization. It reduces the cost by improving the efficiency of resource utilization, especially for large data sets. Third one is dynamic adaptation. Unlike manual clustering, liquid clustering dynamically optimizes data over time, adjusting to patterns in your data as they evolve. So, how to perform liquid clustering? To perform liquid clustering, we will need to enable data lake optimize function with additional patterns or parameters and settings that allow the clustering mechanism to function automatically. While Delta Lake doesn't have an explicit liquid clustering command, the concept involves optimizing tables in a way that data is clustered efficiently over time. So let me give you the command for liquid clustering. So we are going to be creating a new delta table that is optimized for liquid clustering. So let's write percentage SQL and create table in the delta catalog. Delta catalog dot raw dot. So this will be the new table name. Let's give external table and let's give liquid clustering. And we are going to be using the delta. So using delta and where we are getting our data from. So as select asterisk or all from our DML table. So we are going to be using the same DML table. And now let's run this. Okay, there is, so it's delta lake catalog, not delta catalog. That was the issue. Delta lake catalog. I just copy this name. It's same. Delta Lake catalog dot raw dot external table liquid clustering. Now it's fine. Let's run this. And our command ran successfully. So what this command did was it created a new table with the name external table liquid clustering in our Delta Lake. And it populated with the same data as the external table DML that we created before. So this table is created in a way that it can later be optimized with dynamic clustering mechanisms. So let's optimize this data or this table with dynamic clustering. So we're going to use the command percentage SQL, and we're going to optimize this data, optimize and delta lake catalog, sorry, delta lake catalog. And instead of DML, we are going to be using liquid clustering. And then we are going to use the same Z order by, and let's order it by product ID. So now let's run this. So the optimize command here is used to reorganize the new data in our new table, and we applied Z order clustering by product ID. So Z order helps in organizing the data physically on disk in such a way that the product ID columns becomes much more efficient for query by filtering or sorting or anything we want to perform, any query we want to perform on our new table. Liquid clustering will monitor the table and adjust how the data is clustered as the new data is added. Now let's perform the auto optimize. It is optional, but we should learn how to do that. So Delta Lake also provides the option to enable auto optimization features to dynamically optimize data based on evolving patterns. So this can be enabled through configuration. So let me give you the command percentage SQL. Let's give set and spark dot databricks dot delta dot optimize dot, okay, it's not z order by, we have to give optimize write enabled, write dot enabled, and we are going to give this as true. And in the next line, set, and we are going to give the same but with auto optimize and enabled. So let's copy it and here give auto optimize with, okay, there's, let me first write it, then I will explain. Delta dot auto optimize dot optimize right equals to true. Let me check it again. Spark delta auto optimize dot enabled equals to true, and spark databricks delta auto optimize right equals to true. So let's run this. So it ran successfully. So what it did was it enabled the auto optimization for delta tables, meaning that delta will automatically optimize the data as writes occur without requiring you to manually run the optimize command. This is useful for tables that you see frequent updates and large amounts of data. So after running these commands, we will have a new delta table with the name we created, and that was external table for liquid clustering. And that data is optimized using Z order. And we will see improvements in performance of queries that filter or order by the product ID column. And the table will be dynamically managed by Delta Lake, meaning that it will optimize itself over time as more data is written into it. So let me give you it in the simplest term. Imagine your data is a giant pile of books on a shelf and you need to find a specific book quickly. So if the books are just randomly scattered around, it's hard to find the one you want. So liquid clustering is like an intelligent system that automatically arranges these books based on the genres or author that you often look for most. So over time, it learns and organizes the books even better. In this case, the Delta Lake, this intelligent system helps you organize your data in a way that make queries like finding all products of a certain type faster. The more data you add, the more the system keeps organizing it without you needing to do anything manually. And why should we create a new table? So, creating a new table allows you to start fresh with optimized storage, especially after making optimizations like Z order we did on our previous DML table. So it also gives you more control over the structure. So once the table is optimized, the queries will run faster because data is well organized, reducing the time it takes for system to find and process our data. And the new table can automatically adjust changes in the data pattern that so that we don't need to recluster it manually in the future. That is called dynamic adaptation. In this video, we are going to learn about structured streaming, in Databricks using Delta Lake. So, what is structured streaming? Structured streaming is a scalable and fault tolerant stream processing engine that is built on top of Spark SQL. It allows you to process data as it arrives in real time using Spark's unified API. And with structured streaming, we can define queries against our streaming data just like you would for batch data. And Spark will handle the complexity of processing the data in a fault tolerance and distributed way. In structured streaming, the input data is treated as a series of continuous micro batches, and the output is generated periodically. The Spark session processes this data incrementally and generates the results, and the results are then updated and are consistent. So, what are the key features of structured streaming? So, the first one is end to end tolerance. The Spark generates guarantees that the data will be processed at least once and the errors or the failures can be handled gracefully. Second one is exactly once processing. So we can configure the structured streaming to guarantee that each record is processed only once. The third one is real time data processing. Structured streaming can ingest and process data in real time with minimal latency. Next is unified API. We can use the same API, data frame or dataset API for both batch and streaming workloads. So, how can we perform structured streaming in Databricks using PySpark? So let me give you the code. The first thing you have to do is set up the streaming source. So in structured streaming, the data sources are continuously monitored for new data, and the stream processing engine this data as it arrives. For example, you could be streaming from a Delta table, Kafka, file system like S3 or other sources. So here we will be using the Delta table. So let's start with the code. We have to do some imports. So let me give them. The first import is the Spark session from PySpark. PySpark.sql import Spark session. And next import is we are going to import everything from PySpark SQL functions. Yep, not colon, just everything. The next thing is to create a Spark session. So let's give Spark equals to Spark session dot builder dot app name. Let's give any name, structured streaming engine. Let's give structured streaming example. And then dot get or create. The next thing we have to do is define the streaming input source that will be our delta table. So let's give input df spark dot read stream format, and the format is we are using delta, and then dot table. So we will give the name of our table that was delta lake. Let's just copy the name of our table from up here. So we are going to copy the liquid clustering table. So let's copy this name, delta lake catalog dot raw dot external. Let's paste it here. Now let's run this. So let it run. Okay, it's ran successfully. So what it did was the read stream What it does is it reads the data from a streaming source, and format delta, it specifies the source format, in this case that is the delta lake, and the table specifies the delta table to stream from. Alternatively, you could use stream from other sources such as Kafka or file system or socket systems. Now that our streaming data is set, we can define the transformation logic, and we can apply the transformation logic like you would for any batch queries. Let's say we want to filter records where production ID or product ID is greater than a certain value. So let me give the command. Let's give filtered underscore df equals to input underscore df dot filter, and we are going to apply a filter where input df and input df inside there, what we want is the product id, product underscore id, and where product id is, let's say, okay, it should be in double quotes, so make sure, and double quotes where product id, let's me check what exactly the product ids were so that we do not get any error. Okay, so 1 2 3, nope, the product id was 65555. Let's give product id greater than 100. That way we can get some output. Let's give 100 and let's run this. So we have applied this data frame, and we can also apply any data frame or SQL operations for our transformation. Now let's display it. Display filter df. Let's run this. Here you can see we have output and it's trying to read the data as we go. And currently, because our data is fixed and is not streaming, so it has displayed all the results of the data with production ID or product ID greater than 100. And then it has also created charts as well. So let's interrupt this so that it doesn't take up all our resources. Now the next thing we have to do is define the output sink. So we need to define where we want to the process data to go, which is referred to as the sink in the structured streaming. Some common sinks include delta lake tables, Kafka, output consoles, and files. And if you want to store your result in a new delta table, we will do the command. So let's use filter df dot write stream, and we will give multiple options. So we will give format. The format is delta, and in the next line, the output mode, okay, append. So it will append our data, the new data. Now option. So the option we are going to give is checkpoint location, and then we will give the location. So let's give slash mnt slash delta, and then again slash checkpoints slash, let's give new table checkpoint. Okay, there are two slashes, so that will cause an issue. and let's close it. The next thing we want to give is the table. So let's give dot table, and the table we are going to give is delta lake catalog dot raw dot, okay, there are two dots, streamed output table. So let's run this and see what happens. Okay, there was an error. Let's check extra. So this was the issue. Let me give the quotes inside, and there's this extra, and I have run this, and it will take a few seconds to run. So in the meantime, what this does, the write stream function, what it does, it writes the process data to a streaming sink, and the format delta, it specifies the output format, that is the delta table in this case, and the output mode append specifies how to handle the incoming data. So in this case, the new data is appended at the end of the existing table. The next option inside checkpoint location. So a checkpoint location is required for fault tolerance. It allows Spark to keep track of the data, of what data that has been processed, to ensure no data is lost or duplicated. And the table, it specifies the name of the delta table where the result will be written. So let's wait for it to be executed properly. So we have to interrupt it because as long as the input stream keep producing data, this will keep on running. So let's interrupt it to not waste our resources. And the next thing we are going to perform is uh, we will start the streaming query. So once we have defined the input, transformation and output, what we need to do is start the streaming query. So let's move on to the next cell and type the command. And the command goes as query equals to filtered df dot write stream, then dot format. The format we are giving here is delta. Then we are going to give the output mode, append, and then after this we are going to give the option, and option will be the new table checkpoints, pretty much the same that we did. And next we are going to do is the table. So we are going to defining the raw streamed output table, and let's run this. So what this will do is it the start streaming query and begins processing the incoming data. Okay, there's an issue. And so this will start and process the incoming data. So we also have to interrupt this after a few seconds. So because we do not have any incoming data at this point, but in your case, it would be the thing you want to do. So this was the command and how you can start the streaming query. Let's interrupt it to not waste our resources. Okay, our job has been interrupted. Now the next thing we want to do is monitor the streaming query. So we can monitor the progress and the status of the streaming query by checking the status in Databricks. So let me give the command. So the command is pretty simple. So we have to give query dot status and run this. So our data is already been stopped, so it will give false result. But if you have a continuously streaming data, you can get the and the output here as well. So there are a few more things. We can wait for the termination of the query. We can use, let me give it here as well. We can use query dot await termination, and this is what we can use. And what if you want to stop the streaming query? We can use query dot stop. So this is the command for that. So, and we do not need any additional infrastructure. So if you are streaming from a Delta table or a Delta lake, so we do not need any additional infrastructure other than the Delta tables themselves. So Delta Lake provides the necessary infrastructure for handling transactional consistency, fault tolerance, and versioning. So for fault tolerance, you need a checkpoint location. So this is called checkpointing. This is where the Spark will store metadata about processed batches, and it allows the system to resume the last successfully processed batch in case of failure. And if you're running structured streaming on a large scale, make sure your Databricks cluster has sufficient resources like CPU memory to handle the continuous stream of data and processing. So what we have right now is real-time process data. The output will be continuously updated in a Delta table or whatever sync you chose, and that will contain the process data. The data will incrementally be updated as new data is ingested. And if you're monitoring the query, you will get a status of how much data has been processed, whether there are any issues with the streaming process. So in conclusion, structured streaming in Databricks using PySpark allows you to easily process real-time data with a similar API to batch processing while handling the complexities of stream processing under the hood. By defining the input source like Delta Lake, transformation logic, and output sync, you can set up a scalable, fault-tolerant streaming pipeline. Make sure to include checkpointing for fault tolerance and consider cluster resources for large-scale streaming workloads. That's all for this video. Thank you.